Hello boys and girls, Mr. Marek back with you again. In this video we're going to learn nuclear physics. Honestly, if Homer Simpson can do this, so can you. We're going to start out by kind of reviewing the structure of the nucleus, which will probably be a review from chemistry, and then learning why the nucleus is stable. So first, a little bit of review. Remember that the nucleus of an atom is composed of two different kinds of particles, which we have named protons, which have positive charges, and neutrons, which have negative charges. Together, we call these particles nucleons. And so both protons and neutrons are considered nucleons. Remember that the number of protons, which we will also refer to as the atomic number, determines the identity of the atom. So, for example, oxygen always has 8 protons. If you have something that's got 9 protons, you would call it fluorine. Remember, that's how the periodic table is organized. Different atoms of the same kind could have different numbers of neutrons. Those different things are referred to as isotopes. So if you ever wondered why the minor league baseball team of Springfield is called the Isotopes, it's got to do with nuclear physics. Recall the definition of the term mass number, which we're going to give the symbol A, is simply the number of protons and neutrons added together. We might also refer to that as the nucleon number, or number of nucleons, since both protons and neutrons are nucleons. So, here's a quick example. There are two common isotopes of chlorine. One has 18 neutrons, the other has 20 neutrons. If you grab a periodic table and you find chlorine on it, you would see it's the 17th element, which means that its atomic number is 17. So the way that we represent that, when we write the symbol for chlorine, is we would put the atomic number as a subscript in front of the symbol. So we'd write it like this. So doing some real quick math, the isotope that has 18 neutrons would have an atomic number of 35, 17 plus 18. And we would just write that as a superscript in front of the atomic symbol. And then doing some quick math there, the atomic number will be 37 for that isotope. When we write that as I skipped ahead too fast. Write that as a superscript in front of the atomic symbol. And so we would have two different kinds of chlorine, two different isotopes, chlorine 35, chlorine 37. You may, in your lifetime, have heard about quarks. Protons and neutrons, even though in most situations we can treat them as being a fundamental particle, aren't really fundamental particles. They're made up of things called quarks, and quarks are fundamental particles. Other fundamental particles we may know and love are electrons. And then later on we're going to learn about the particle model of light, and we'll call those particle photons. Those are also fundamental particles. Quarks are charged, but their charge is a fraction of the elementary charge. Remember, the elementary charge is the charge on a proton, which is 1.6 times 10 to the negative 19. So as a simple example, here is a chart giving you the properties of different quarks. Different quarks are referred to as having different flavors, which is kind of weird. And the whole naming thing behind quarks is just weird in general. But notice the column on the right where it gives you the charge on the quark as a fraction of the elementary charge. And so the composition of a proton would consist of two up quarks, which have a charge of plus 2/3, and then a single down quark, which has a charge of negative 1/3, and you can see how that would add up to 1. Whereas a neutron is 2 downs and an up, which you can see would give you a charge of 0. That's a little bit beyond what we actually need to know for this particular class. What we really need to know is that protons and neutrons are made of quarks, and that quarks are charged with some fraction of the elementary charge. So those are the two kind of facts we need to know there. Okay, let's talk a little bit about nuclear stability. Because at some point in your life, when you were in chemistry, maybe even when you were in physics and you started learning about Coulomb's law, you might ask yourself, how in the heck can you cram a bunch of positively charged protons into such a very tiny space? How tiny? Well, the radius of a nucleus is approximately, depending on how big of a nucleus it is, 10 to the negative fifth meters, which we might refer to as a femtometer. And the reason why that should surprise you is because when you put two positive charges very close together, they should exert a very large electric force on each other, and that force should be repulsive. We can calculate how large that force is using good old Coulomb's law. The elementary charge, again, 1.6 times 10 to the negative 19th. It's two of them, so squared. And then over that small distance of about a femtometer, would give you a force of 230 newtons, which doesn't seem a lot to you, but to a proton, that is a gargantuan force. I've always liked that word, gargantuan, so rarely have a chance to use it in a sentence. So, obviously, there's got to be some other force present in the nucleus which can overcome the electric repulsion due to those things being charged. And so that force is referred to as the strong nuclear force. The strong nuclear force, we have discovered, is an attractive force which will act between protons and protons, protons and neutrons and neutrons. So the strong nuclear force is an attractive force which will hold all the things in the nucleus together. The thing about it is that the strong nuclear force is very short-ranged. It's got a effective distance, if you will, of about a femtometer. It doesn't drop off as distance squared like the other forces that we've studied. It kind of just goes away all at once you separate the things by more than a femtometer. The nuclear force does not affect electrons at all. And so in the future we're going to see situations where protons and neutrons could possibly turn into electrons, and those things aren't going to be held in the nucleus at all. And then it's the range of the strong nuclear force, like the fact that it can only exist over about a femtometer, which determines the size limit of the nucleus. And so from chemistry you may remember the size of the periodic table and how once we get down to the 1/10s, it just kind of ends. The fact that the nuclear force only exists over 1 femtometer will tell us why such heavy elements really can't exist. The electric force would overcome the strong nuclear force, and those things would be very quickly torn apart. So things which have, and by things I mean nuclei, which have small radii, like at the upper end of the periodic table, typically have a neutron number which is approximately equal to the atomic number. And so I can say that the number of neutrons is N and that the number of protons is Z. Larger nuclei have typically more neutrons than protons. The reason for that is necessary to increase the net nuclear force to overcome the added electrical repulsion. And so a handy-dandy chart will look something like this. The red line represents a 1-to-1 ratio between neutron number and proton number. The blue line represents what is actually observed in nature for stable nuclei. So notice at the very beginning those two lines overlap, and then after a while, basically right around this area, the two lines start to diverge. And so again, these are things which are stable. The red line represents a hypothetical 1-to-1 ratio. And you can see the farther or the more protons we get, the bigger the gap between those two lines is. And so that's kind of a general trend. Initially, small radii you need about the same number of neutrons to make the nucleus stable. But as you get about above atomic number 20 or so, then you need more neutrons than protons to make the nucleus stable. Okay, so suppose for a second that you had some raw protons and raw neutrons. So like they weren't bound to anything. They weren't part of a nucleus. And then suppose you went off and you measured what their masses were. Which, by the way, you should be able to tell me how to measure the mass of something like a proton. We know how to do that already. You would get values like these two right here. I kind of wrote those in kilograms. And notice there's something on the order of 10 to the negative 27th. Now imagine that you had a single helium nucleus. A helium nucleus would have 2 protons and 2 neutrons. And you did the same thing. You measured its mass, which again is something we know how to do. If you did that, you would measure the helium nucleus's mass to be 6.64764 times 10 to the negative 27 kilograms, which should come as an absolute shock to you. I'll give you a second to let you collect yourself. Now the reason that should come to an absolute shock to you, because the masses don't add up. As soon as you saw that, you probably mentally added those 2 numbers at the top. Like 2 protons would have that mass, 2 neutrons would have that mass, and you mentally probably add them together to get a number that looks like that, which is more, than the measured actual mass of a helium nucleus. Somehow, when we put the nucleus together, some of that mass was lost as we put it together, which should seem weird and strange to you. This missing mass we refer to as the mass defect. So, this is weird. We have the mass that the helium nucleus should be, right there, and then the mass that it is, and they don't agree with each other. So something has happened to a little bit, not a whole lot, but it's still a little bit, it's still measurable amount of mass. So to be able to explain that, we need to learn just a tiny little bit about relativity and some Einstein physics. So Mr. Einstein's theory of general relativity predicted, through like equations and stuff, that mass and energy are equivalent to each other, meaning that they're 2 different forms of the same thing. To kind of put that another way, mass can be converted to energy and vice versa. And so that idea may seem kind of strange until you see the relationship that actually predicted that. And you're like, oh yeah, I've seen that before. In the E equals mc squared equation, E stands for energy, m stands for mass, and of course c stands for the speed of light. Now notice that the speed of light's a ridiculously big number, and then when you square that you get an even more ridiculously big number. And so these energy numbers are going to be very, 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 very large. It's a lot of energy we're talking about here. So when we formed the helium nucleus, because it's stable, its energy was lower than it was started when it was just parts of protons and nucleus. So in other words, energy was released. To kind of put that in a picture form, here's the free protons and neutrons, minding their own business, and then somehow we force them together into a nucleus. Energy is going to be released as a result of that process. If we do the math, the free protons and neutrons had that mass. The helium nucleus has that mass. If we subtract the 2, we get this mass. This is the mass that was converted to energy. So if we want to know how much energy was created, we could use Einstein's theory of relativity equation. So just multiply that missing mass by the speed of light squared, and we would get something like this. And so you may look at that and you're like, 10 to the negative 12th joules, whatever, that's tiny. But compared to the size of a neutron, or excuse me, a nucleus, helium nucleus, that is a gargantuan amount of energy. This energy is released. Now it's released in either kinetic energy, like the helium nucleus moves as a result of that, or it's released as radiation. We'll talk more about the different kinds of radiation and how that works later on. What we need to be able to do for today is figure out how much the energy was released from the missing mass. Another term for that energy that's released is called binding energy. And the reason that it's called binding energy is if you were to take the nucleus and try to pull it apart, basically undo that process, you would have to put in that much energy in order to break it apart. So if we took our picture and we turn it around, if we took our helium nucleus and we added that much energy to it, then we could break it apart into just unbonded free protons and neutrons again. So again, because it's the energy also needed to tear the nucleus apart, we call it the binding energy. It's the energy that went into binding it together. It's also a measure of the stability of the nucleus. The greater the binding energy per nucleon, it's like per proton, per neutron, the more stable the nucleus is going to be. And so the best way to illustrate that is with a graph. So this graph is a graph of binding energy per nucleon, so that's the y-axis over here, versus the atomic or nucleon number. You could also do it versus atomic number. And the thing that I want you to kind of notice is that the very small element, hydrogen, is at the very low end of the chart. And then more importantly, the high end of the chart would be iron. So iron's up here. It's got the highest binding energy per nucleon. It's kind of the top of that chart. And so things on this side want to get smaller. Things on this side want to get bigger because iron is the most stable nucleus. We'll talk about how those processes actually occur later on. So, I'll give you a couple of different units that you can use because kilograms and joules are really too big for nuclear physics. And so commonly, instead of using kilograms for mass, we use a unit called the atomic mass unit, or AMU. At some point in chemistry, you're probably taught this and you've probably forgotten it since then. 1 AMU is simply 1.66 times 10 to the negative 27 kilograms. It's pretty close to the mass of the proton and the neutron. A better unit for energy that we can use is called the electron volt, which has a symbol E capital V. We'll talk more about the definition of that later on. An electron volt has a energy in joules of 1.6 times 10 to the negative 19 joules. Notice that number is the same as the number for the elementary charge. Now if we take Einstein's equation, E equals mc squared, and we solve it for m, we would get E over c squared, meaning that I can express an AMU in terms of electron volts and the speed of light. And that's typically expressed like this, that 1 AMU is equivalent to 931 mega electron volts of energy. And so that kind of incorporates the whole divided by the speed of light squared thing in the equation. We'll look at an example how we use that later on. It's basically a useful shortcut. So real quickly, looking at the front side of our formula chart we get to use on the AP exam, notice the conversion factor between an atomic mass unit and electron volt are given to you, as well as that neat little shortcut that allows you to go from mass defect straight to the binding energy. Just multiply it by 931. You've got the binding energy in mega electron volts. So let's look at a quick example. If you look up iron 56, so we would write iron 56 like that. It's got an atomic number 26, and a mass number of 56, you would find that its actual mass is 55.934940 AMU. We want to know what its binding energy is. How much energy is it going to take to rip this thing apart? If you look up the mass of a proton and a neutron in AMUs, you'd get something like this. And then we need to figure out how many protons and neutrons that iron atom actually, iron nucleus actually contains. And so 26 is the atomic number, so 26 protons. The 56 represents the mass number, so that's the protons and neutrons together. And so if you got 26 protons, 56 total, you can do some math and get 30 neutrons. So the expected mass, for lack of a better term, multiply 26 by 1.007276 AMUs, and then 30 by the mass of the neutron. And if you did that, you would get something like this number of AMUs. That's obviously bigger than the actual mass of iron 56. So the mass defect, which we might call delta M, just subtract the mass we should have gotten from the mass that we actually get when we measure the mass of iron, and we would get something like 0.488986 AMUs. So let's use that to find the binding energy. There's two approaches we could take. The first approach is to take our mass defect, convert it to kilograms. So 1 AMU is 1.66 times 10 to the negative 27 kilograms. So we'd get that number of kilograms right there. And then just plug that into Einstein's general relativity equation, which would give us something on the order of 7.3 times 10 to the negative 11 joules. Pretty big number for a nucleus. Now the other approach that we could use is to take the number of AMUs and simply multiply it by 931 megaelectron volts per c squared. And so when we do that, we would get a number like 455 megaelectron volts, which is equal to 455 times 10 to the 6 electron volts. And that could be our answer. It is perfectly legit for us to express our answer in megaelectron volts. But to show you that it's the same, let's go ahead and convert that to joules. So again, there's 1.6 times 10 to the negative 19 electron volts in a joule. Hang on. Kind of wrote that backwards a little bit. Fix that real quick. And so the EVs would cancel out. And we would get a number like this. Basically, 7.3 times 10 to the negative 11 joules. So there's some slight differences in the way we would round the intermediate numbers, namely the 931. But you can see that we get essentially the same answer either way. So again, it's perfectly okay to leave your answer in mega electron volts. That's kind of actually preferred in a lot of situations. Okay, so let's kind of review real quick. Can you do the following? Explain the structure of the nucleus, what it's made out of. Can you identify different isotopes and atoms? Like if I give you the atomic number and the mass number, can you tell me how many neutrons there are? Describe a quark. It's got, the elementary charge, some fraction of it as its charge. Can you describe the strong nuclear force? Short-ranged. Can you explain why the nuclei are stable as a consequence of the strong nuclear force? And then lastly, can you calculate and explain the binding energy for a nucleus? And so, yeah, that's quite a lot of information. A lot of it's review. Some of it's new, and we'll continue to see new stuff. I just remember, if this guy can do it, so can you. So I'll see you in class next time. Till then, ta-ta.